Okay, so in the last video, we defined the derivative of a function f at a point A to be, this is the notation, f prime of A, and we defined it to be the limit if I take the average change of the function over an interval from A to A plus H, and I take the limit as H goes to 0, then this is called the instantaneous rate of change of the function at A, and we call this the derivative of f at A. And I should say, I didn't say this in the last video, but I should say this is only defined if this limit exists. So this limit potentially might not exist. And if it doesn't exist, then the derivative is not defined at that point. So if the limit exists, then we say this is the derivative at A. So I want to say what this means graphically. This is almost identical to one of the videos in the previous section. Let's say I have a function f, and let's say this is my point A. And now if I look at, let's call this A plus H. So this is my interval of length H here. And if I look at what is f of A plus H minus f of A, well, it's the change in the y value. So it's this negative y value. I started up here and I'm ending down here. And then if I divide this by H, this is giving me exactly the slope of the line through this point, through these 2 points, the slope of the line through these 2 points. And now if I take H going to 0, then this secant line is going to change. The 2 points are going to get closer and closer together. And as I take the limit, as H goes to 0, the secant line is going to approach this tangent line. And so this derivative, so if I don't take the limit, each one of these is the slope of the secant line. And as the 2 points get closer and closer together, the secant line gets closer and closer to the tangent line. And so as I take the limit as H goes to 0, this limit is going to be the slope of this line. So it's the slope of the tangent line. And sometimes we say that this is the slope of the function at x equals a. So before, in our time before calculus, we only knew how to say what is the slope of a straight line, right? We take rise over run. And if we wanted to say what is the slope of a line that's curved, it's completely reasonable to say, well, it's the slope of the tangent line at that point. And so now this is a way that we can define slope of a function at a point. So if this derivative exists, then it's the slope of the tangent line at that point, and we can say that that's the slope of the function at that point.